Okay, initially the apparatus is grounded as the two leaves in the apparatus are close together, and in this process the wand is gaining electrons from the fur, and in attempt to the two leaves move farther apart, giving the apparatus a negative charge, and because the two leaves have a positive charge, they seem to repel. And now Garrett will ground it.
And this will take electrons away from the apparatus and put them back in the ground, so they'll both have a neutral charge and go back together.
And now to prove a positive charge of the apparatus, we can use a different stick and different wand and a piece of silk, which takes electrons away from the wand. And by doing this, the two will repel again, giving the apparatus both leaves a positive charge. And because positives repel, and in this example it's clearly seen that they're repelling, we can see that the apparatus now has a positive charge. And after Garrett grounds grounds the apparatus, the two leaves move closer together, hence the state of the apparatus is now neutral.
So I'm using this silk to remove the electrons from this wand, making it positively charged. And so when I transfer the positive charge through conduction to the system, the leaves should spread apart, as you see, and it is now positively charged.
And to again prove the positive charge of the apparatus, we can use this stick that is now negatively charged, as it is giving electrons from this piece of fur. And now the two sticks should come together, as you can see through the conduction. And because opposites attract, and the leaves were previously positively charged and the wand was negatively charged, and they attract, so they should come closer together as seen in the example. Alright, so currently the apparatus is grounded in that it's in a neutral state, and making the balloon into a negative charge by rubbing the fur against it. It gives the balloon more electrons, and here we are trying to exemplify the process.
It's not touching.
Oh my god. The induction between, and now the two are positively charged, and as we moved the balloon away, we can see that the two leaves are now spreading apart. And to prove that the leaves are positively charged, we can use a positively charged wand to show that if this goes near, the leaves should repel, and that is seen without contact.
And also, if we use a negatively charged wand and put it near, they should draw closer together.
You go stroke it like once or twice. Yeah, like that. Yeah, nice. Cool.
And that's positively charged. I'm using this silk to take all the electrons away from the wand, and then as I put it next to the system, it will cause
And
the
the
leaves
ground
to repel.
takes the
The
electrons. So
ground will add electrons to the system, causing it to be negative. When we pull that away, we unground it, and so this is now negatively charged. And we can prove that by adding electrons to the balloon and using induction to add negative charge to the system, causing the leaves to repel since it's already negative.
Nice.
Okay, so to measure the transfer of electrons, one of the previous situations was reconducted, and in this case it was the black wand being rubbed against the piece of fur. And to get an exact measurement, the iPad was used, and the data was recorded through one of the apps. And the exact charge of the black wand after being rubbed against the piece of fur came out to be negative 32.03 nanocoulombs, or 3.203 times 10 to the negative 8th coulombs. And this can be seen through the spike in the graph at time equals 3.1 seconds, as there's a sharp downward spike in the graph. And this value was later converted into the number of electrons that were transferred, and this could be done through a simple dimensional analysis in which negative 32.03 times 10 to the negative 9th coulombs were converted into electrons, and in one electron there's 1.6 times 10 to the negative 19th coulombs. And so in the end, the group deduced that 2.00 times 10 to the 11th electrons were transferred as a result of the black wand being rubbed against the fur.